All right, everybody. This is kind of a continuation of our previous notes there about the relationships in a balanced equation. So what I've done here is on the top right of my iPad in Notability is I highlighted this here so I can see all the pages in my packet. And then when I select the page that I was on, I can select and these little three dots come up. I said add a page, and that's what I did over here. So I need a little bit more space based upon what I had. All right. So that's what I have here, and then I copied my equation again. So what I'm going to do is further talk about the relationships here that we're seeing. All right. And so here's our equation again, and we talked about that these coefficients, they represent moles. So even though that there's no units that are listed after these coefficients here, we know that these represent moles. So until that becomes really second nature, what you may want to do is write that in, that these numbers represent moles. Oops. Minimize that there. Now this is all well and good, and it tells me that if I want to do this reaction as it's written, my recipe says that for every 2 moles of C2H6, I'm going to need 7 moles of O2 to completely react. Now, that's great, except for I can't go to a scale or measure out moles of a substance. So one of the things that we'll learn about is well, I've got scales, I've got balances, and so I need to know how much would I weigh out of each of these chemicals, all right? So if I wanted to think about these, I could convert these moles into grams. And so what I would use is my periodic table, and I would use the molar masses to be able to figure out what I have. So first thing I would do is I need to figure out my molar mass of C2H6. So for my formula, I have, and so I'm going to ignore the coefficient right now. My formula says I have 2 carbons and I have 6 hydrogens. So I would go to my periodic table and I'd look up the molar mass or the atomic mass that's on there. And I'd probably round as a general idea to 2 decimal places. And so for carbon, I'm going to take 2 times the molar mass of carbon, which is about 12.01 grams. And for hydrogen, it's about 1.01 grams. And so I plug that into my calculator, and it tells me that I have about the molar mass of C2H6 is about 30.08 grams for every 1 mole. Now, because I have the 2 in my equation, what I want to do now is multiply this molar mass by 2. All right, so that's what my next piece is. I'm going to take 2 times that molar mass of 30.08 for every 1 mole, and that equals about 60.16 grams. So in other words, if I want to perform this equation, this is how many grams I would actually weigh out to make this reaction happen. Now I need to do the same thing where I figure out how many grams is equal to 7 moles. All right. So for oxygen, okay, we look at the molar mass of oxygen on our periodic table, and it's about 16 grams per mole. All right. So we know that there's 2 oxygens there. 1 oxygen has a mass of 16 grams per mole. And then there's 2 of them based upon the 2 there. So what that means is that the molar mass of O2 is equal to 32.0 grams for every 1 mole. Now here's where we go and we incorporate our coefficient now. Now that we have 7 of them, I'm going to take 7 times my 32.0 grams for every 1 mole, and multiplying that out gives me 224 grams. So what that tells me is that if I wanted to perform this equation exactly as it's written, then what I would do is I would have to measure out 60.16 grams of C2, 60.16 grams of C2H6 and 224 grams of O2. And when I mix those together, they would both get completely used up, and I would make 4 moles of CO2 and 6 moles of H2O. Now, if you want to pause the video, I want you to follow this same process for your 4 moles of CO2 and 6 moles of H2O. I want you to figure out the mass of 4 moles of CO2 and the mass of 6 moles of H2O. So go ahead and pause the video, and then we can go through it together here. All right. So hopefully what you figured out for CO2, you've got the 1 carbon and 2 oxygens. So your molar mass, so I'd have 12.01 from your carbon. The 2 oxygens, as we saw from our previous one, is 32. Okay, or you could say it's going to be plus 2 times your 16 grams per mole. And then, so if you plug that into your calculator, it equals 44 grams per mole. And then we have from our equation 4 moles, so I'm going to multiply that value by 4, and that equals 176 grams roughly. I might have shortchanged myself, 0.01, so this is 0.04. And so I would produce in this reaction 176.04 grams of CO2. Go ahead and label these grams of O2, grams of C2H6. And for water, my molar mass of water is going to be, do that in blue here, with our 2 hydrogens plus our 1 oxygen. I write O's like that so it doesn't look like a 0. So I have 2 times 1.01 grams plus my 16 grams from oxygen. So we get 18.02 grams per mole. And then multiplying that by our number of moles, which is 6. Let's see. So I would have 6 times my 18.02. And that's going to give me, let me move some things over here a little bit. That's going to give me 108.12 grams. All right. Now, if we were to look at these and add these up, what we ought to notice is that our law of conservation of matter, shrink this down a little bit, okay, and this is our green line dividing up our reactants and our products. What we ought to understand is that our balanced equation follows our law of conservation of matter. So if we add up our mass of our reactants, and the mass of our products should equal out to be the same. So 60.16 plus 224 gives us 284.16 grams. This is the mass of all our reactants together. And for our products, we add these together. 16, there's a 4, put there, 284. So we can see by applying our ideas about molar mass to our equation, we can see that the mass of our reactants and the mass of our products, they're equal to each other. And so in our balanced equation, the law of conservation of matter does apply. All right. So this is another way of looking at our balanced equation and sort of understanding what it tells us and the relationships that are present there. So in summary, we can look at our balanced equation in terms of a small scale with molecules and atoms, but most of the time we look at it in terms of moles. And then for moles, what we want to recognize is that in order to actually act upon this recipe and actually perform it, measure it out, carry it out, not only do we have a relationship that involves moles, but we also have a relationship that involves mass. All right, thanks for watching.